Hi, everyone. I come to you from the depths of a very, very, very deep rabbit hole. Just a few weeks ago, irresponsibly close to giving this talk, my friend Robbie Lyman and I finished up a pre-release for Neurovolume. This is a library that writes VDBs, which are sparse, volumetric data structures mostly used in 3D graphics. The writer is written in Zig, more on that later, with no dependencies. The library is in Python with very few dependencies: NumPy, PyTest, Ziglang for compiling, and a neuroscience library that I use for testing, which I aim to remove once my testing suite is up to snuff. You can use it to render things out like this. My main focus is real-world scientific data, and I've been dog-fooding it with a toy fMRI visualization pipeline. More on that later. In this talk, we're going to address how I ended up making this thing, what exactly a VDB is, how to write a VDB with Neurovolume, my library, and some under-the-hood details of this library. At the end, we're going to build an irresponsibly janky fMRI analysis and visualization pipeline. I do not come from a traditional background in programming. In 2021, I was running a small VFX company, mostly working on music videos and advertisements. That's my producer, Noah, in our office, and these are some random photos I found from sets that I ended up on. One perk of having my own VFX company is I got to write off all sorts of experiments on my taxes. I rented a LiDAR scanner for a week just to see how it worked. LiDAR scanners shoot out lasers that capture these massive point clouds of the world around you. My friend Alex was finishing up college and needed an internship credit, so technically being a business owner, I just hired him as my intern, and we ran around New York scanning buildings and things. If you ever need to do something like this, here's a tip. If you buy a high-vis jacket, everyone just assumes you're doing something really important. So we would run out into the streets and hold up traffic in Manhattan, and all of these New Yorkers would politely drive around us. It was great. On our real gig, I learned about VDBs. I think this is my first time using them, was on this music video. And these are really different than point clouds. As you can see here, the VDBs are the clouds in this video. The plane and things are traditional meshes. They're really different than point clouds, which I showed you earlier. They're volumetric, but a point cloud is really understandable. It can be represented as just a list of XYZ coordinates and then maybe RGB for color. Even if you can't code, and at the time I couldn't, you can open it up in a text editor and see what's going on. VDBs were so much more mysterious. VDBs, you need a hex editor to look at, and even then, they're sort of hard to decipher. The name seems like it should be an acronym, but nobody knows what it's supposed to stand for, including the inventors. They're volumes, but they're super efficient. And you can render out all sorts of things that are traditionally hard to see in 3D, like clouds and water and smoke and explosions. They have this thing called grids, which you can map to different parts of your rendering pipeline. The file usually gives you some attribute like temperature or flames or density, which you can combine in a shader editor. And these are what make VDBs really art directable, meaning you have a lot of control over how they look in the render engine. They're also easily animated. This is an example render from Jenga FX. But unlike point clouds, which are not very realistic looking and not very computationally efficient, I've never seen any real-world data rendered with a VDB. We could get a mesh from real-world data with photogrammetry, and you can get a point cloud from LiDAR scans, but I hadn't seen a lot of VDB examples out there. Unlike meshes, VDBs represent the interior of things. Like they're a volume all the way through. They're not just hollow. And unlike point clouds, they're very efficient and can show incredibly fine details. And there's so many things that would benefit from being represented this way, right? I'm thinking about anything with fine, weird detail and multiple discrete substances all kind of mixed together. Think about a mycelium network. These are the underground fungal networks that sprout mushrooms and keep plants alive and do all sorts of mysterious, wonderful things. Imagine being able to render one of these or a simulation of one of these in a VDB with the rocks and the roots and the dirt all separate from the mycelium itself. You could even make the mycelium glow to illustrate it if you were trying to say something specific. Think about being able to render a weather system with clouds and rain and pressure and glorious, highly detailed 3D animations. Spoiler alert, people are actually already using VDBs for this. The original scientific paper mentions medical data as a great use for volumes and thus a great use for VDBs. Maybe if we could illustrate all of these things in this really, really fine detail and in an art directable way, we'd begin to understand them all better. So these are all the things I was thinking about as a visual effects artist, but never really got to explore until I learned Python. I started this project because I needed something to talk about during job interviews. It's a few years ago, and I'm mid-career change, and I'm trying to leave the film industry to write software full-time. So this little project of mine has a couple of requirements. I just need something that I can toss up on GitHub. It needs to be easy, because I'm pretty new to programming. It should utilize some of my VFX skills. And even if the code is basic, there should be some visual component that looks impressive, right? And I'd heard of these things called fMRIs, functional magnetic resonance imaging. And all of the information that I had came from really dubious sources like podcasts and conversations with people at parties in the psychedelic therapy space. And my vague understanding was that an fMRI could show thoughts as they appeared in the brain. And I look online, and most of the renders of fMRIs are kind of lackluster. And so I have this great idea for my portfolio. I'm going to get some fMRI data from online, and then I'll pull out the brain anatomy, and I'll pull out the thoughts, whatever those are, the red globby things that I see, and then I'll put them on two different separate VDB grids, and I'll combine them together into one VDB, and then I'll render it, and I'll add some camera movement, and it'll look really cool, and then I'll have something I can talk about on job interviews. And from first principles, and from the Python libraries that I see on PyPy, this looks like it should be really easy. Like VDBs are gridded volumes, and the nibabble gets me a NumPy array, right? And it really doesn't look like it should be that hard, right? OpenVDB, which is the industry standard for writing VDBs, also has a Python library. So I figure I can just, do this. But I immediately run into two problems. First, the PyOpenVDB library is kind of an afterthought to this giant C++ code base that sits underneath it, that only graphics programmers really seem to understand. This makes the Python library really not portable, and you need some kind of containerization to run it. And at the time, I'm a total noob. I don't know how to use a package manager, so Conda and Docker is way outside of my skill set. And the second problem is, what is a thought? Like what is brain activity? What are fMRIs supposed to be showing in general? The more I think about it, the less sense it makes. So I decide to start with the containerization issues. Luckily, my friend Zach Lipp knows Docker really well, so he helps build out a container for OpenVDB. Important to note that he did the vast majority of work on this. While Zach is putting on the finishing touches to the Docker container, I start experimenting with some ways to get MRI volumes directly into Blender by building them out as shaders. Eventually, Zach gets the Docker image working well enough that I can start working with VDBs from real-life sources. I don't remember where this data set came from. I think it's a CT scan of a human head from the Visible Human project. But there's some issues. I was still really inexperienced, and maintaining Docker images was hard. Just adding another Python library led to all sorts of bugs that I had no idea how to squash. Getting the data into a Docker environment and a VDB back out in a way that could interface quickly with Blender was a huge pain. So around this time, my friend Nathan, who suggested I do this talk, put me in contact with some of his friends at NASA, AJ, and Atusa, who were using VDBs in some of their work. And they had these pipelines where visualization artists needed to render specific data. VDBs were being used as the intermediary, OpenVDB being not very portable, or PyOpenVDB being not very portable, and sort of an afterthought to the C++ code, made it really hard to integrate VDBs into these workflows, especially ones that span both scientific computing and VFX. So we have this huge hole in the ecosystem. We need a lightweight VDB writer that you can just pip install. This would solve all of my problems, and it sounds like it might solve some problems at NASA, which is really cool. So I decide to build this. I start by following this great blog post from Jenga FX, where they walk you through how to make a minimal VDB writer It's not sparse. It doesn't have grids, which are those channels I talked about earlier. But it is a VDB. You can load it into Blender and render an image. I'm writing this entire thing in Go, so I don't have those nice Python libraries we all love. But thankfully, the nifty file format is pretty digestible and well documented, so I follow along there just to write a parser. And I managed to get some VDBs written. Here's some fMRI data playing in my as a VDB in Blender. But there's some problems. I vibe coded this entire mess. And I wrote it in Go for some reason, and it's full of unsafe Go, which being a relatively new programmer, I can't tell if this is a limitation with my project or with Go itself or something that my code is doing that it shouldn't be doing. And I go in and I try to add grids and tiles, but it's just a giant spaghetti mess and I don't even know where to start. Tiles are what make VDBs sparse. They make sure that a VDB ignores long stretches of uniform data, like where a volume is empty or otherwise the same scalar values like the inside of a cloud. This makes the files themselves a lot smaller by pruning unnecessary branches of the data structure. Grids, as you remember, are those attributes I talked about earlier, the channels that allow you to pull out specific parts of the volume like heat or fuel or density. And this is what makes VDBs art directable. I need both of these for my project, but I don't understand my code base because I over-relied on LLMs, and no matter how much I throw the giant original scientific paper at ChatGPT, nothing good comes out on the other end. So I decide I need to rewrite this entire thing from first principles as outlined in the original scientific paper that specifies the VDB as much as humanly possible. And this is what Neurovolume is today. The project aims to be portable, easy to use, with as few dependencies as possible, and should leverage the existing domain knowledge of the user. For that last point, I decided to rely on one very important dependency, NumPy. This is our main intermediary. I decided on this architecture after trying to parse netcdf files, which are used a lot for satellite data. I was feeling really, really confident after writing a parser for nifty files, which I used for neuroscience, and they're just a big predictable list of bytes. But netcdf has all sorts of branching paths and things, and it's a lot harder to write a parser for it. And I realized that there's all sorts of other libraries and data types out there that I'm never gonna have enough time to write parsers for. So I decide to just ask the user to get the data into NumPy. Most libraries and pretty much every domain has a workflow that uses NumPy, so no one has to rewrite their pipelines. Basically, if you can get it there, Neurovolume can get you out of VDB. Robbie Lyman, our first contributor, finally got these tiles working in Zig. I exposed the prune value in Python. This can be accessed in channels, which hold all of the information that you need to make a grid. Higher pruning leads to sparser but more degraded volumes, as you can see here. But even a very low prune value can still save you a lot of disk space with no degradation to the final render. Here you've got the Stanford bunny at 189 megabytes in a NumPy array or on disk, and without any visual degradation, we still shave off about 40% of the disk usage. And this is something you can render right away. You can just throw it into a piece of VFX software and it works. You don't have to inflate it or anything. It's not compressed in that kind of way like a zip file. You can also interpolate the data to fit multiple timescales without choppy playback. Above, you can see some fMRI data that was acquired at 0.5 frames per second. It's playing back at 24 frames per second. And the crossfade between them is smoothing things out. This is really useful for data types that don't conform to real world or real-time data acquisition timestamps. Because of NumPy, we can apply this to other domains. Here, we have some weather simulation. Here we have some weather simulation data, and we've broken out the rain and clouds into different channels. And these get added into a sequence, and when you save the VDBs, they become named grids. Here's the final render with the shader node graph on the right. Neurovolume uses grids to map the clouds and data density to rain and an emissive texture. Sorry, the grids here are being mapped to density and emission. The emission is rain, and then I put some color on it so you can see kind of the intensity of the rain at a given point. This is really, really fun to play with. I tried some globe projections too at a lower resolution. I'm not a climate scientist, so take all of these visuals with a huge grain of salt. But it's really fun. Let's talk about what's under the hood. Python is a great interface, but we need a really fast systems language to actually write the VDBs. And for this, I chose Zig. I really like Zig. Unlike Rust or Go, it's not really opinionated, so I'm never breaking the language with unsafe code. This is great for relative beginners like myself. I can just focus on how computers work, not on how the language itself works. There are a lot of people in New York who are really into Zig, so it's easy to find help. It's really fast. There are breaking changes all the time, so you have to update your code for the new releases that come out. But I think it's worth it. Zig exposes the C application binary interface, which means it can interface very nicely with Python via the standard library C types. So ideally, we could have a pipeline that kind of looks like this, with just a clean Zig library, and then using the ABI to automatically generate, using a heuristic from the ABI to automatically generate some Python code that handles all of the memory management. Unfortunately, the existing heuristics for this, like Ziggy PyDust, are lagging a bit in the language updates. And I'm really hesitant to add a dependency to this project, even a dev dependency, because the entire point of this is that there's as few dependencies as possible. So in reality, it's not that simple. We start with our Zig library, and here's the grid section of our VDB writer that Robbie wrote. I'm really happy with his code. Robbie did a great job. And I one day want this to become a standalone Zig library to support the, in addition to the Python library. But then we have this file that's called croot, which packages all of those functions in a way that can be cross-compiled to C. This is really fiddly work, and it should be automatically generated with a heuristic, but for now, in our code base, it's an LLM-generated nightmare. Once the C code is compiled, Python has to read the C functions, but it's all just terrible boilerplate with really fiddly specific arguments that I have to specify with the C archetypes. So this too is an LLM-generated nightmare. On the top, though, I do get to write some Python functions that encapsulate the memory management so the user doesn't have to think about it. This is one of my favorite parts of the entire project to write, trying to figure out what level of abstraction a user needs at a given point in their project is a really fun challenge. In the future, I obviously hope to generate all of this translation layer with a heuristic, not just LLM-generated nonsense. But this gets out actual VDBs. It works. We've got a decent minimum viable product, and we don't need to use Docker. You can just pip install this thing. But I still have this portfolio project that I want to build. I've used neurological data, but I don't have anything that resembles an actual analysis or visualization pipeline. At this point, this original idea has become a total side quest to the actual journey of building a VDB writer, but I decided to get into it nonetheless. To understand fMRIs, we need to understand MRIs, which are magnetic resonance imaging. This is an oversimplification. I am not a radiologist. MRIs spin a giant magnet around a person or plant or anything else that isn't itself magnetic, and they create different images, which represent different types of tissue at different voxel densities. A common type of image for representing brain anatomy is the T1 weighted image, which renders fat as bright and water as dark, or fat as higher scalar value in the voxel and water as a lower scalar value in the voxel. fMRIs are a time series, like a video. It uses something called bold contrast, which is the blood oxygenation level dependent effect. Here, oxygenated blood is light, deoxygenated blood is dark. Bold scans are much quicker to acquire, which means you can take them in a time series. That's what gets you a video. However, they are much lower resolution, so usually they get overlaid in a T1 image so that you can show the subject's brain, so you can show where in the brain the actual oxygenation is happening. But why do we care about oxygenation at all in the brain? It's because after neurons fire in the brain needs oxygen in that area, so this cardiovascular system floods the brain with oxygenated blood in that area. This creates a large spike of oxygenation, supply outweighs demand, and it happens about 5 or 6 seconds after the neurons fire. So This is really removed from measuring brain activity, let alone cognition, let alone, quote unquote, thoughts, whatever those are. You're measuring a correlate to neurological activity at low resolutions, at low frame rates, about 5 or 6 seconds after it happened. So in order to pull out any kind of meaningful information from this, you need to take an average of a very large data set. Again, this is hugely oversimplified. I'm going to come back to this later, but basically when you download one of these, you pull out these TSV files and they show, I grabbed a study from, with a bunch of data online. We had a subject looking at images of people who had different facial expressions, and it's run over and over and over again, so you have enough data of the brain responding to these facial expressions to get any kind of meaningful information out of it. The problem is this data is still pretty noisy, so you have to denoise it. Subjects move around a lot, so you need motion correction. There's all sorts of other steps that need to be applied to this, which goes into something called the analysis pipeline. And the problem with this is if you fiddle with one of these steps slightly, you can get vastly different results. This was illustrated in a seminal study called the dead salmon paper. As a joke, some scientists stuck a dead salmon in an fMRI machine and ran their study on it, and according to the analysis pipeline, the dead salmon showed brain activity. A different analysis pipeline or a comparison between multiple analysis pipelines might show a more truthful result. So I'm not going to make any neuroscience strides here today, but maybe if I build a little toy version of this, it'll be a good starting point for people who will. Looking at an fMRI analysis pipeline, I realized something. All these steps have film industry equivalents. Time slice correction looks a lot like deinterlacing old video footage. Motion correction is just 3D tracking. Denoising is often done with Gaussian blur. Oddly enough, I was surprised to learn this. I'm sure that there's more advanced denoising techniques out for bold responses, so if anyone knows anything about that, please come find me after this talk. Not to mention, all the linear algebra is the same for both of these domains. So once I realized this, it's pretty easy to start building little visualization tools on top of parts of the analysis pipeline. Blender, which is an open source 3D software, has a Python scripting terminal, so I can leverage a lot of the techniques and libraries that I've been using to build plugins. This one here ingests nifty files and just spits them out as VDBs using Neurovolume. So I think I've finally got enough information to build my original idea. I still haven't finished this. I want to see if I can build a toy version of an fMRI analysis pipeline. It needs to basically be a single subject, so I don't need to worry about brain morphology. It needs to pull out the relevant data via the method of subtraction, do some pre-processing, which is just going to be Gaussian blur, and combine these together in a VDB. So I get a data set from OpenNeuro, which has tons of terabytes of data, and anyone can download it for free. When you download an image, it still has all of the same anatomy. And so I use this library called ants to separate the brain from the rest of the anatomy. This is a process called skull stripping. If you look here, you see my LSP bugging out, and it is doing this, and I don't care because I'm well past needing this for a job interview. I'm working on it for this talk in this very conference center. So ants gets rid of the brain anatomy, and now I've just got this nice T1 brain separated from all of that. Great. There are these TSV files that come with the brain, and they tell you where in the study the bold image was taken and for how long. Note that the stimuli come up in different order so that the subject isn't anticipating them. I pick happy as my stimulus and as my experimental condition, and neutral as my control. And I use the metadata from the nifty file to extract this, to extract all of this with NIBabble and figure out where in the sequence the stimuli occurred. I take an average of the spatial data in each frame and store it in a NumPy array. And then I subtract the control from the experimental, add Gaussian blur, which I average up together and just yeet into Neurovolume, which is the easy part. And then pull that into Blender, where I texture and render it. Notice that the grids in the shader editor. I send this back to my PC in New York via a Dropbox file, and it's kind of choppy and a little bit pixelated. So I add a blur along the temporal axis, which feels kind of redundant to the interpolation that I've already done, but whatever. And then I increase the Gaussian values. And this is last night. I get a low quality version of it. But I realize, at least according to skimming Wikipedia, that I see some activity in the visual cortex back there. And that might just be me massaging the data. But onwards we go. This is last night, so I set off another render, and I pray that my cat doesn't walk across my keyboard. And it comes back fine, so I throw it into After Effects this morning to get out an H.264 file, and here we go. If you look, you see a lot of bold response. Oh, thanks. If you look at this, you see a lot of the bold response is happening outside of the brain itself. And some of it looks like it's happening just in random pieces of air, like outside of the human itself. So if you glean nothing else from this very, very silly render, it should be that bold responses are incredibly noisy and they show neurological activity in all sorts of things like dead salmon and the air around the subject. There are a million reasons to not do what I did. OpenVDB is a great library, and our little VDB writer hasn't even begun to reach the performance that it achieves, let alone all the features that it has, like the many variants of VDBs. The sane solution to the friction introduced by this unruly C++ codebase would be just to learn Docker. Furthermore, an incredibly ergonomic pipeline that lets you fiddle around with statistical models until a desired result appears invites people to massage the data. It lets users muck around with their data until they see what they want to see. And making this potentially p-hacked data really easy to visualize in a flashy 3D render might not be the best idea. I worry about this. But I think it's worth it. What I worry about more is who we shut out when we ask our users to contend with wobbly towers of abstraction. Most of you sitting in the audience here have glorious Turing-complete devices stuffed in your backpacks. If someone shows you a render of galaxies or brains or weather simulations, you should be able to run the code yourself on your machine and understand how it works. If the software that we write is only accessible to engineers, then scientists might not replicate it. Furthermore, we miss out on the cross-domain synthesis that Python, in its beautiful accessibility, provides us all. The closer our code gets to first principles, the more dependencies we eliminate, the more portable these projects become. And this portability is what empowers coders from diverse domain backgrounds to build new and wonderful things with the discoveries that you have made. This is what Python is to me, the common ground for artists, scientists, hackers, engineers, and anyone else with a free afternoon and a laptop to build atop each other's discoveries. I hope my little library is a step in the right direction. I hope I have just 30 seconds to thank everyone who helped out on this project. Thank you to Robbie Lyman for writing all of the really hard Zig code and fostering the Zig community in New York City. Thank you to Zach Lipp for writing the original Docker container. Thank you to my wife, Bia, for supporting this crazy idea every step of the way. Thank you, Alex, Bia, Charlie, Div, Manny, Peter, for watching rehearsals for this talk and giving feedback. Especially thank you to Manny and Div, who suggested I rehearse at all. Anything good about this talk is thanks to them. Thank you to Stone for squashing some really early, terrible VDB bugs. Thank you to the real scientists who endured all my endless questions and were generous enough to give me feedback, those being AJ, Atusa, and Tion. Thank you to Nathan for suggesting I do this talk. Thank you to everyone who listened to early versions of this talk at the Zig Day meetups and the Macro Town Hall. Thank you to the Recurse Center in New York City for introducing me to almost every person on this list. All the neurological data here came from a study on emotion category and face perception. It's available on Open Neuro. Come find me this afternoon if you have any questions, comments, gripes, compliments, whatever else. Thank you so much.